Welcome to the next video in the Real Analysis video series, and in this we're going to prove a theorem and do an exercise. So the theorem is this thing that I've been saying for a little while now, and I'm actually going to make good on it by proving this so-called LUB property, or least upper bound property. And so this is the property that if you have a set of any real numbers, non-empty and bounded above, then with the set of upper bounds taken from the real numbers, the supremum is guaranteed to exist. In fact, it exists and it is unique. But the uniqueness thing, I don't even prove here because it follows so easily from an earlier theorem. The earlier theorem is that the minimum and the maximum of any set, when they exist, must be unique. Well, the supremum, as we've already said, is defined in terms of the minimum of a certain set, namely the set of upper bounds. And so as long as we guarantee that it exists, it follows immediately that it is unique. Now, I am noticing, actually, that I gave a proof here that is perhaps a bit more complicated than it needs to be. So I'm going to actually redo the proof off to the side. So, let X be, right? So we're going to let X be a set of real numbers, non-empty, bounded above. But then what I want to do, and I will do at least one part of what I did before, which is let U be the set of all upper bounds of X. And then what I want to do is argue that this has a minimum. If you think in just kind of like a diagram, like let's try to think of a set X. Now, sets of real numbers can get really weird, but let's just imagine that the set X, is like from here to there, right? I don't know, this could be like 0 to 1 or something. And then maybe, I don't know, it goes from 2 to 2.2 or whatever. I'm just making up random things just to make up a semi-random set X, right? So our X is like the union of these intervals. I don't know, maybe we'll make it inclusive on this end or something like that. But, just imagine a set X. I just want to draw this so that you can then look at what the set U is supposed to be. And so if our X looks like this, then the set U would include this point, 2.2, and then extend out here to infinity, because all of these points would be some upper bound of the set X. And, we know that X is non-empty and bounded above, so that this set U has at least one element. And so what we want to do is argue that U has a minimum so that it basically follows that the least upper bound exists. I mean, that's pretty much just immediately the definition of the supremum of X. Well, here is where the completeness axiom, right? Think about the completeness axiom that we introduced at I think the very first video of this video series, laying out all of the axioms of the real numbers. And up to this point, we have not yet touched the completeness axiom. And that one said that if you have one set entirely below another set, then there is at least one point in between them. So we're going to use that. I think, it said that there is a point C in between. Well, X here is entirely below U, right? X is entirely below U. It's easy to prove that. I mean, it almost is just immediate from definitions. Maybe it even is just immediate from definitions. But so I take it that that is pretty well established. And so X is entirely below U, so there exists a point, right? So there is a real number, we'll call it C, such that for all points in X, right? By the way, sometimes when we're thinking geometrically, we call elements of X points. We don't always have to, and I won't necessarily always be consistent about doing that, but something like when a set has something that can be rendered geometrically, then sometimes we call it an element or we call it a point, and we don't even really think about the fact that we're using two different words for the same thing. So they're just synonyms. Anyway, so for any point in X, then X is less than or equal to C. And for any U in the set of upper bounds, we have that X is, I have that backwards. Oops. So, right, because this point C should be above X. So X less than or equal to C, and for any U in the set of upper bounds, C is less than or equal to U. By the completeness axiom, we know this value C exists. Clearly, from this, it is already an upper bound, right? C is an upper bound of X, which immediately tells us that C is an element of U, since U is the set of all upper bounds. That's nice because this is part of what we need to establish that C is the minimum of the set U. And this right here already says that it is a lower bound, which is the other part that we need, right? C is a lower bound of U. So those facts together establish that C is equal to the minimum of the set U, which is to say that it is the supremum of X. Okay, so that I think is a nice theorem. It all kind of comes together so cleanly. Let's do an exercise, the equivalence of the LUB and completeness, right, the LUB property and the completeness axiom. So what this says is that, in fact, the converse is also true. If a set of numbers satisfying the ordered field axioms has the LUB property, then it must satisfy the completeness axiom, right? So basically they're interchangeable. We could have removed the completeness axiom and replaced it with the LUB property, and we would have exactly the same conditions. So, right, because up above we proved that completeness implies LUB. Here we're going to prove that LUB implies completeness. So that is your exercise. Prove this claim, and I'll show my proof in the next video.